you see that? Yes. Okay. Right. So I'm actually going to be going through quite a lot of material today. I know I've already mentioned this, but I'm going to be going through quite a lot of material. I'm going to send out the video to this ASAP. So it's not going to be very well edited, but you'll have the material there, so that if you need to come and reference what I've gone through, you've just got it there. The other thing is, I'm going to put a pause in at the 45-minute mark after I've demonstrated creating of two devices. If you have got to the point where you just can't take in any more information anymore, and it's just like information overload, feel free to leave at that point. I'll be spending another 15 minutes after that going through another two devices, creating another two devices. But like I say, you'll get all the video and stuff. If you've got stuff to do on plant, whatever, it's okay. You know what I mean? If you can't take in that information. So, what we're going to be doing today. So, I'm going to go through briefly symbols and reference designators. I mentioned the reference designators last week. Can you remember what they are? You'll know.
The letters that go before pressing a component number.
Yeah, exactly. So they're the little unique identifiers, basically, of components, like R12, U3. We're going to talk very briefly about the actual circuit that we're going to be building, because it's just useful to have a little bit of background on what we're doing. This is an electronics course, but I wanted to just give you a bit of an understanding of what we're doing. So, and then we're going to go into the main bulk, which is learning how to create devices in Proteus. I forgot a piezo device. This is Joe pointed this out. Piezoelectric devices don't fit into any of the libraries that you've already created, so you want to create a new piezo device, piezo library. Can you tell me what piezo means? What the effect of piezo, the piezoelectric effect? Okay, so what happens is in certain crystalline structures, if you apply a pressure across the structure, it generates a small potential difference, and we use that for fire alarms, the really annoying loud buzzer, that's a piezoelectric buzzer. Computers when they beep, and crystal oscillators for microcontrollers, processors, that kind of stuff. So we need that extra one in there. So this is the default set of symbols that Proteus sort of comes with. They're quite standard. I'm going to go through a few. Does anyone know what this thing is? Transformer. This thing?
Inductor.
Yeah. I'm not going to ask you what that is because it says it. And so the rest of it. So they're pretty simple, they're pretty intuitive. If you are creating a device in Proteus and you don't know what symbol to use, you can head into the library, find one that's similar, and use that as a base template. It's the easiest way to sort of keep all your designs homogeneous across the board and with other people as well. The kind of odd thing about this is the way that we do Zeners and Schottkys. So what you might have seen before is a Zener diode has like this little zigzag thing at the front on the cathode, and a Schottky has this like curly thing at the front as well. So in Proteus, we've got 1 bar on the cathode for a Zener and 2 bars for a Schottky. So it's just worth bearing that in mind. It's kind of it makes it so that you're not using tiny little features of diodes to identify the two. So reference designator, this is taken from Wikipedia. Unambiguously identifies a component with an electrical circuit, electrical schematic, or on a printed circuit board. Now, again, if you're creating a device and you don't know what reference designator to use, don't know what letter in the alphabet to use to put in front of it, you can go to Proteus libraries, pick one out that's similar, and then that's the letter that you can use. If you still can't find this like odd component, you can actually go onto the Wikipedia website, and this is a table that I just pulled from there, and it tells you what the more standard, reference designators are used, so you can use that as well. Right, so a little bit of background on the headphone amp that we're going to make. So put an asterisk there with a twist. So this is based around an op-amp amplifier circuit. So the op-amp is here. And what we've got after the op-amp is a current boosting sort of mechanism. So these are common collector transistors in a push-pull configuration. Doesn't really matter so much. It's very analogous to Class B amplification. I don't expect you to know the differences between Class A, Class B, Class AB, Class D, Class C, whatever. But I'm going to explain a small limitation and how we overcome that limitation. So op-amps are excellent devices, very versatile, but they typically don't have much output current. So if you want to drive some big beefy headphones, you're not going to have much power behind it. So we're using a couple of transistors to boost the current. In the circuit on the left, transistors require a certain amount of voltage before they even turn on. They've got this like dead zone, and it's about 0.7 volts. Can anyone guess where that 0.7 volts might come from? What other things have 0.7 volts before they do something? Diodes, yeah. So transistors have essentially they've got PN junctions in there, they've got volt drops, they have to overcome that diode volt drop before it does anything. The problem with that is if you're listening to really quiet audio, for example in headphones, or you've got tiny little earbuds that only need like a handful of millivolts to run, you might be within that dead zone, and therefore they don't even produce anything. There's no output. If you go beyond that output, you get this horrendous thing called crossover distortion. I've got a slide to show you what that looks like. How do we overcome that? You could completely bin off the topology and choose something else completely. But there's an interesting way. I've taken this from a Renesas application note. On the right, what's the difference between the circuits of these two circuits?
Where the feedback loop comes from.
Boom. Feedback loop. Can everyone see that? Yeah. So the difference is that these two transistors are part of the op-amp feedback loop. The op-amp, without going into detail of what op-amps do and why they can do this, the op-amp's going to compensate for that little dead zone. And that helps to alleviate most of the crossover distortion. On the left, you can see this is the blue signals are the input signals, the red traces are the output signals. So the Class B amp, you can see these flat bits, that's the dead zone. In the middle trace, we've mostly overcome it with op-amp compensation, and you can see that it's a nice, smooth waveform until you zoom in very, very close, and then you can see that there's still a little bit of that leftover error. I don't know, I've not built a circuit yet. I don't know whether that's going to be audible or not. I've got a feeling that it might still be audible. It'll be good to test. We're going to be able to switch between the modes, so you'll be able to hear the difference and see the difference on a oscilloscope if you want to do that. There's an extra little upgrade that we can do to this circuit to eliminate it entirely, and I will tell you what that is next week. Right, so now we're going to get into the sort of gubbins of the thing here. So first thing we want to do is set up a template on Proteus. Now, what's a template? Why do we need one? This is what Proteus looks like if you don't have a template. It's just a flat page, there's nothing on it. There's no information about the author, what page it is, all that kind of stuff. So we're going to set one up. Now, again, you're going to get all these slides, so you don't have to write all this down, but to set up your template folder, I should have really done it last week, but I forgot. You go to System Settings, Template Folders, click the little plus, if you remember where the library thing is, it's just the window above that, or the section above that. Add this, which is from the network drive, and then restart Proteus. If people are doing this, if this video's out there and you haven't got access to this, this directory, Proteus comes with default templates, so you can use default templates as well. New project wizard, right? Demo it, okay? So now I'm going to start demoing stuff because there's just too much to write and put into, PowerPoint slides. So cool. So new project. No guesses for how to do that. File, new project. Now what I'm going to do is, sorry, 1 second. Copy that. Put it there. Now I know where what directory I want it. So you can put the path to wherever you want. In your Proteus folder, you can create another one called projects and stick it in there. And we're going to call it Headphone Amplifier. We do want to create a schematic from a template, and these are the templates that you'll have access to if you've added that library folder. So I'm going to go with A3 landscape, but also you could use the default one as well. We do want to create a PCB layout, and we'll use a simple default template for that because we will be modifying it a bit. This next screen shows you the stack up. If you remember last week, I was talking about PCB stack up and how many layers that you can get into a PCB. Well, you can define them to the point where you can control the dielectric constant of the FR4 material. You can put the thicknesses of copper, it can all be defined. We're not going to get into that much detail, so we can just click next. This is defining, remember the vias I was talking about? You can go through one layer, all the layers, you can bury them, they can be blind. This is your drill span information. So if you've got all these different types of vias, you can put the drill spans in this box, but every single hole on our circuit is going to go straight through the board from top layer to bottom layer. So we've only got one type of drill which goes through the entire stack. So I'm just going to leave that as next. That should become a little bit clearer when we look at this. So this diagram changes based on the options that you choose. So we've got one type of through hole, which is through the whole thing, and 2 layers. We don't want to create any firmware. Finish. That's your PCB layout. Absolutely nothing on there yet. And we've got our template. The template is not editable on this normal screen, so you can't really, do anything with this. If you do want to edit it, and this is a slight aside, you can go to template, go to master sheet, and now you can see that it's all editable. If you want to create a template, you can edit the master sheet, go to template, and then click save design as template, and then you can create your own, basically. But we're not going to do that.
How would you change your template once you've already made your project with that one?
Once you've already made your project,
Yeah.
you can do this.
Oh,
literally.
one.
Yeah. So every project contains a master sheet. And if you want to edit the template at any point, you can go back to the master sheet, modify it, and then everything that you save applies to the entire project.
Okay, so I can just load it in.
Into other projects afterwards.
Yeah, so I've made one project already, but I
Yeah.
can put a template on. So if I need to load in.
Yes. Yeah. I see. So you're thinking about applying. So I think apply styles from template. That'll allow you to retroactively fit a template to an existing project. Okay, so I'm going to go back to. So if you want to, so we're on the master sheet now. You don't spend much time there because this is just the background for every single sheet that you've got on your schematic. To go back, you go to design root sheet, and then this takes you back to the main schematic editing page. One thing that's pretty cool, right? So we've got a bunch of information here. You can see every @ symbol. That means it's actually dynamically linked to the project properties. Now I'll explain exactly what that means. If we go to design, edit design properties, and we start filling out this, such as headphone amplifier, document number and revision, I use as like a revision code, so major version, minor version. Author, D. Beckett, press OK. You have to press OK and then you have to click somewhere. See that change? It dynamically brings in all that information, so it's quite nice. Go to edit and then design sheet properties. Now the sheet property is properties based on the actual sheet that you're on. So I'm going to call it full schematic. Press OK, click somewhere, boom, appears. So the sheet, obviously, you might have a power supply page, you might have like a microcontroller page, but because we've got such a small circuit, it's all going on here, so I've just called it full schematic. Does that make sense?
Dan, what was the first one you went to get your name updated? Design and...
Edit design properties.
Design.
So it's these two options at the top there. Yeah. Cool. Template's done. Go back to this. I've done that. Project properties. Already done that. Device tutorial. Oh look, we've got through the whole thing. We haven't. This is the longest part. Right. So part one. So it's split into 2 parts. This because there's quite a lot to get through. We're going to sort out our default keyboard shortcuts because Proteus doesn't come with like copy and paste. You have to put in copy and paste shortcut if you want to use it. So you do want to do that. You only have to do it once. we're going to place components from the Proteus libraries, the default libraries, and modify them, and then save them to our libraries. We're going to find some real components on Farnell, so that's actually an important practical lesson. How do you find your components? What do you search for? How do you pick ones that aren't going to go obsolete in 3 days' time, especially in sort of the current climate? And then we're going to check data sheets. So we're going to find a component, open the data sheet, check that our footprint matches the device that we're going to buy. Make sure your pins are in the right place. Because if you create your circuit, you get it made, and you've messed the pins up on your footprint, everything's connected to the wrong point, or maybe the device doesn't fit. So this is all quite, important to do. So here, this is what the goal's going to be. So by this time next week, what we want to have is the set of these components ready to go. What I mean by ready to go is you've added them to your own libraries, and they've got all the information within each one to be able to buy it, source it, and we've checked all the pins and stuff. I'm going to demonstrate 4 of these, and I'm going to have a small break after 2, and at that point, if you want to head off, feel free, and then I'm going to demonstrate another 2 as well, just to give you a bit of breathing space, really. Right, so I've got a bit of notes with me here so I don't forget. So the first thing is our keyboard maps, because we just need to do that. So keyboard map, system, set keyboard mapping. There's only a couple that we want to do. So you scroll down, this is all the different menu items. So I'm scrolling down, where it says schematic window, edit menu commands. You see it says cut, copy and paste. Press Control-C in there, click assign, copy, paste. I meant X in that. Okay, cut, copy, paste, done. And we scroll down in this thing here. Now I'm just using the mouse wheel over to do it quickly. Mode selection commands. The only 2 extra ones we want to do is selection mode, press S. No, click in there, press S, assign. Component mode, click in there, press C, assign. Done. That's all we need to do. The S and C part, by the way, on the up, can you see that? These 2 things? S and C switch between these 2 modes. I'm pressing S and C there. So that's selection is just if you want to move stuff around in your schematic. Component is when you want to place components and play around with them. Right, I'm going to place some default library components. So you get into component mode, press P over here next to the devices text, and then it opens up on the wrong screen. And then we're going to play some stuff. This is the part that I did before and all the libraries were gone. I was like, oh, that's great. I can't place any components. So I'm going to take, these 2 parts are actually very similar in the library, but I'm going to take the op-amp one here from the op-amp library. So you press OK on it, and then you click once, and then you place the component.
How did you zoom in on that so quickly, Dan?
Oh yeah, mouse wheel.
Hovering on the component?
No, anywhere. So if you want to zoom over there, just mouse wheel in.
Okay, thanks.
No probs. Every time I click P, it opens. Right, MMBT 3904. Place that one. That's one of our transistors. Place BT 3906. See that? Place the MMBT 3906, which is its PNP counterpart. We are going to place a ConSil 2. ConSil 2. Just to give a very, very quick background on this. There's a lot of single inline and dual inline connectors that you can just use. These are very standard 0.1 inch pitch pin headers that you can just, they're used all over the place on circuit boards. 0.1 inch pitch headers are just very, very commonplace. So if you want a 2-pin one, SIL single inline, two pins, it's just there, ready to use, which is quite nice. A 7812, 7812. We're going to use one of them. Can anyone guess what that is? Yes. 7912. Anyone know the difference between these two? Yeah, too easy. Right, now I'm going to place a component that I fully intend not to use in its current form. Okay, so I'm going to go cap. I'm going to place a capacitor. Okay, the only reason why I'm placing a capacitor is so that I've got this symbol on the circuit. This is one of those cases where I just want to use the symbol. I'm not bothered about what it is because I'm just going to fully change it. So I've got the symbol for that capacitor. I'm going to place a 1N4148. Does anyone know what that part is? Yeah. I'm going to take it out of the diode library, like so, and then I'm going to place a pickaxe socket. This is kind of a bizarre one. Nope. I'm placing this. This is intended as a programming header, but what it actually is a 3.5mm TRS jack. So you know what 3.5mm headphones?
Yeah.
Yeah, it's a headphone jack. So I'm going to adapt it because the footprint's done, and I'm going to check the footprint against the datasheet, like we should do for everything. But I'm just going to adapt it and use it as our headphone jacks. That's all of them to place. Right. The first thing is that you've got this like text sort of label here. We don't ever really use that text label. So what I'm going to do is go to template and then set text styles. It's hard to say that. I've said it loads now out loud. It just sounds like text styles. Anyway. Properties. And then go to not visible, uncheck that, and all that text just disappears. Right, so what I'm going to start doing is I'm going to start moving components over to the right hand side that we've completed. Okay, so we know which ones are done. So the Consil 2, I'm only using that as a feature on the PCB to connect one of those 9-volt head. You know the 9-volt like batteries that have got the clippy header thing. When they come off 2 wires, I'm just going to use that to solder onto the board. So there's no component to buy for it. There's just nothing. It's just a PCB feature. So we're done for that part. Easy. So the first thing that we're going to demonstrate is the op amp. So this NE5532, pretty standard part. First thing we want to see is, now I'm just going to quickly check something. Yep, got that. Right. The first thing that I want to check is the contents of it. Now, can you see that this component doesn't contain much information about it? You don't know where to buy it, you don't know its voltage, you don't know its current, you don't know... There's not much information in the default properties. We're going to change that. So, the first things first is let's find the thing. Which NE5532 are we going to buy? So, NE5532 in Farnell. Farnell's pretty good, it's got a lot of components. Mauser's got even more. DigiKey's got billions of components. So if you can't find it in DigiKey, you can't find it. I mean, you can still look in other places, but you know.
Octopart's quite useful.
Octopart.
Stock.
Okay. I'd never really use it. I might take a look into it.
Yeah, I start using that. That's built into Altium these days.
Right,
So
okay.
It kind of says this is in stock in these places.
Right,
It
okay.
gives you a cost of the bulk.
Oh, excellent. Right, okay.
That's what you're paying for.
Yeah, of course. Cool, so why is this not searching? Come on. Yeah. Have we got that right? It's thinking, isn't it? So all I'm trying to do is search this component. Hmm? Yeah, I mean it's important that we this does work. I've got internet connectivity.
Oh no, this fan out does do this from time to time, Dan.
Yeah?
Yeah, it just...
Try it on a different one.
Might have to, yeah.
As much as Farnell is a great supplier, they are a pain in the arse as a requisitioner.
Yes, they are. The base near Leeds.
Are they?
Yeah, their main
Explains
headquarters.
everything.
Fancy that? Okay, well, whilst that's thinking, we'll find the part somewhere else. Right, so which NE5532 do we want to buy? So I'm going to drill down into the final level category that you can in whichever supplier that you're choosing. If it was, then this wouldn't be working, I feel. Not sure. In either case, which one is it? NE5532 AP. Yeah, okay, right. So the way that I like to find parts is you always keep an eye on the availability. So you don't want to, like I said before, you don't want to end up in a place where you've specified parts and it's not available. So for our circuit, we're going to use a dual inline package, and we're going to use this NE5532 AP. Now you can see that here there's 6,166 in stock. That's quite a good indicator that you're not going to run out of these things. So what we're going to do, we find the part that we want to use, and then we find the data sheet for that. Now, because I've run through this a couple of times, I know that the data sheet for this part wasn't on Farnell. So if that does happen as well, so if the data sheet isn't available on the distributor's website, then just go Google it and find the data sheet because you need it. But here we have it. So this is an audio op amp used all over the place, has been used for a very, very long time. And there's two main bits of information that we want out of the data sheet for now, and that is the pin out of the component. So you can see all the pins here, tells you what pin does what, and then we want to know the package. Now, we've got an NE5532 AP. The A stands for the low noise version, P is the package. So sometimes what you can do, if you do Control F in the datasheet and go NE5532 AP, if you're lucky, it'll locate NE5532 AP. In other cases, you'll just have to decode it a little bit. There'll be information on how to decode what package it uses. This is using the PDIP, plastic dual inline, and it's got package drawing P. So if we go and find drawing P, which is not that, that. So this is our plastic dual inline package. And this is the chip that we're going to buy. These drawings are actually quite nice. And there's two main features that I want you to remember from this right now. You see this gap between the pins? That's the pitch. And the pitch is 0.1 inch. Okay? And you see the gap between the pins here? It says between 0.3 and 0.325. We'll take it as 0.3. So 0.1 between the pins, 0.3 across the columns. That's what we want to remember. Now, those packages are very, very well known and common. So Proteus does have a default package that we can use. What we're going to do is I'm going to send you out this file. And this file contains this information here. This information allows you to quickly add properties to a component. So I've copied the contents of that file and I'm pasting it in the other properties box within the component. Okay? Now, I want to turn this into my own component. I want to create this in my own library. And the way that you do that, the way that you create a new component, is you right-click it and you go to Make Device. This process is going to get very familiar. Right-click, Make Device. And now we're going to start making the device ready for our own library. I'll show you where that text comes in later. It's obvious where that previous text, the stuff that I pasted in, you'll see where that comes in. The device name in this screen is what the library, it's the library name, so you can be quite descriptive. It's not going to appear in a BOM or anything. So I'm going to call this op amp. I'm going to call it a dual because there's 2 op amps in one package. I'm going to call it 10 megahertz because I remember what it was from the data sheet. And I'm going to go plus minus 22 volts. That's a lot of information about that part. So you can search that. That's all searchable. And I'm obviously keeping the name of the part as well, NE5532. It's actually the AP version, so I'm going to put the AP at the end of it. All that is searchable, so good stuff. U, reference designator. If you don't know what it should be, Wikipedia or check the default libraries. U's fine. U's correct for these. We're lucky with this part because the default Proteus library comes with this PDIP part. Do you remember the 0.3 inch and the 0.1 inch? There. So you can already see that this footprint is going to fit. The one thing we don't know, though, for sure, is whether the pins are mapped out correctly. So if we did want to add or edit a package onto a specific device, you click Add Edit there, and then we get this box. So what this does is you can add multiple packages for a device if you want, but in our case, we're going to check that these pins line up with the actual part that we're buying. Just to give you a quick overview here, this little table, you've got positive input, negative input, output. Positive input, negative input, output, okay? And then you've got V plus and V minus, 8 and 4, V plus, V minus. You can see that we've got 2 gates. Why have we got 2 gates? Yes, yes. The dual package, the 2 op amps in one thing, 2 gates. They just call them gates. Could be all gates, could be op amps, could be whatever. There's 2 of them. A and B denote the different columns for, you know, each op amp. And then you see that the V plus and V minus of this number spans all of the gates. That's because this common thing's checked. When you click common, it means that that pin applies to all gates. Right, so let's quickly check the pins, which should be pretty straightforward to do on this one. Oh yeah, when you're inputting, you know those 8 megahertz blah 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 that I put into the library, you want to check that that's actually the case in the datasheet. What I'm saying is don't trust this information here. All distributors get that wrong. You have to go into the datasheet and check the component itself. That can be used as a rough guide. This is where you'll actually find your information. Needed to get that off my chest. Not kidding. Yeah, exactly. Right, so here is pin config and functions. Pretty simple. So if we just remember here, 1 out, so you've got op amp 1 and op amp 2. So you've got pin 1, 2 and 3, out, negative in, positive in. So pin 1, 2 and 3 on the first thing, out, negative in, positive in. You know that those pins are correct. So these pins, these names of these pins come from the pins on the schematic, the actual pins on the schematic. These are the numbers associated with the op amp footprint. Now we're going to check the other one. So op amp 2, we've got 7, 6, 5, out, negative in, positive in. So we've got 7, 6, 5, out, negative in, positive in. It all works. Does that make sense? Yeah. You can also hover the mouse over, and then you can actually see which pin's connected to what, you know, from the schematic to the footprint. And just so I'll show you, see this, if I delete that 5 there, it goes purple when, yeah. So you need to, so that can tell you which is what's connected and make sure they're all connected. Right, we're good there. Assign package, good job. Right, next. You know that custom list that I put in the component before? This has now auto-populated this list. That's why the custom component fields are useful. So I'm going to, mod file is a default Proteus thing. It's to do with simulation. So we don't really need that. So I'm just going to delete the mod file. But then we've got package, value, voltage, blah, 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 blah. All of these fields now are from that custom component script. Package is DIL 08. We've just found that. The value is an NE5532. 5532 AP. and the value appears on the. You see these MMB T3904. The capacitor will have 0.1 microfarads. That appears on your. That actually appears on your schematic. Voltage is. I'll just remember this: plus, minus 22 volts. Everything here should be capitals, apart from if you want to use like smalls for like milliamps or millivolts. But everything else should be capitals. Current. Right. So current. We go into the data sheet. We go to absolute maximum ratings. Did I? Up a bit. Thank you all very much. It's actually not there. That's input current. So we'll have to, if it's not in the absolute maximum, you have to go into the electrical. Right. Output short circuit current. This device. This is just an interesting aside, really. Look at the variation. This is min, typical, and max. Typical, if you imagine like a distribution curve, is right in the middle of the distribution curve. Max and min, you have to, when you're designing something, if you want the thing to work with every single part that you might be able to buy, then you need to work with the max and min values, not just the headline typical, because you might have a situation where some parts work and then some parts don't. For example, the variation, you've got 10, so you might buy one component that's got a minimum, it might only be able to output 10 milliamps. You might have one that can output 60. So go with the worst case. So we're going to put 10 milliamps in that, because you just never know. That's the wrong way, isn't it? Power is not applicable. They'll all come with not checked in the field there. If you've checked it and it's not applicable, just put like a dash, a minus sign. Tolerance is not applicable. The manufacturer, right, so now this is where we flick over here, and then it's Texas Instruments. So, what was that one? Yeah, Texas Instruments. Okay. Manufacturer part number. Right, copy that. No, yeah, that is the manufacturer part number. And then the stockist is Mauser. It's not Farnell, is it? Because it didn't work. And then we go to the Mauser part number. Delete the space. And special. There's nothing special about this device. It's a bit tight, isn't it? Special is used as like if there's something particularly weird about a component. Like it's got a very excellent dielectric that you're using in a ceramic capacitor, or it's got like some bizarre thing about it. You can put it in the special column. It's at your discretion, basically. And then generic tells you, is this part generic? Would you allow the manufacturer of the PCB to swap this part out for another equivalent part? Usually no, some cases yes. So usually no, we're not going to have that as a generic part. If you're not sure, just click no, just say no. I've just skipped past that. This is a data sheet screen. This is for Proteus itself. If you want to save your data sheets with the associated device in Proteus, you can do. I never do. I just go on Google and search the data sheet. This is library information. Do we care about library information? Yes, we do. So you need to have these top two columns filled in, otherwise you can't make the part. So you need to make sure these two are accurate. I never really put the manufacturer in, because you can see the manufacturer in the information that we've just saved into the part, the custom. And then this box here is searchable. So this is searchable information in the library. So if you've built a massive library and you're like, what part was that? It was 40 volts VCE. If you want to add some information about it, you can leave it in there. The default description's good for us because we actually had a default NE5532 part pulled from the Proteus library, so we can leave that as is. And then which library I'm going to put this in? Which library will I choose to put? If I'm adding it to my custom libraries, which one will an op amp go in?
Chips.
Yes, it's an integrated circuit. Done. Easy. So now, this part that's on the schematic is the component from the old library, from Proteus's default library. So delete it. A quick way to delete stuff is press right click twice. Gone. And then you see it's already in component mode. I've got like a pencil as an icon, and I've got my new shiny thingy highlighted in the part picker here. So when I click anywhere on the schematic, that's my part now. That's from my library. I'm going to press S because it's a nice shortcut that we just made, to go to the arrow, double click it. There's all our part. That's all the information about the part.
How do you place the other half?
Good point. So the way to do, so this is a dual device. I'm going to boot it over here because we're done with it. If you want to place the other part, you can either pick exactly the same part out of the library and place it, or, because we've got this new spangled thing called copy and paste, Control C, Control V, you can, and it does the gate there. Now, yeah, go on.
And if you did that again, it would be U2A and U2B and then
U4, because I've already got two. Now, what you can do, and this is quite cool, if you want to change the gate of the part, double click it, and see the element thing here? You can select, because I've got U1 and U4 placed, it knows that those 4 op amps are available to use. So you can just click. I wonder what if you do that. Swap. It swaps it. That's quite cool, isn't it? And then U4B, yeah.
So if you're not using U4, the B part,
Yeah.
where do you place a not connect symbol without getting ahead of myself?
A not connect symbol.
would you leave that off the schematic?
Yeah.
Well, I mean, say you're not using a pin.
What you say on any old part if we're not using a pin?
Yeah, there's usually like a cross you can put on a.
I think place terminal. I admittedly,
Not connected.
is it?
Yeah.
I've never used that,
Yeah.
so I'm glad that I found that on the fly. Yeah. So I suppose you can just put that. You just place it. But if you don't have the,
Okay, I'm following. So if you put the second gate on, would you then draw the connections to the supply rails as well?
you wouldn't have to, because this is actually connected to that.
Yes.
So if you put power, yeah.
Draw them in your schematic, but it would know automatically in your PCB layout, wouldn't it? It
Yes.
wouldn't run 2 routes.
Yes.
It would allow you to do one.
Yeah.
And I guess likewise, if you only place the part A, it wouldn't make you connect anything to the part B pins of 5, 6, and 7, because it knows that they're not connected because you never placed the object.
Yeah.
But if you did place it and you hit the you're not connected pins, then it would know not to route anything, I guess.
Yes.
Okay.
I don't know the function. I don't necessarily know the function of the not connected. It might just be a. Do you know what it typically
It
is?
depends on the package. Like Altium would get very cross if you didn't put the not connect part.
Oh, right. Okay. Okay.
So it doesn't know what to do with the net.
Yeah.
Right.
So it's hanging your design was on there.
Yeah. Got you. I'm not sure if that's the case. I think you can probably. I don't think it checks for that. But I'll test it. I'll definitely test it.
The other thing I was going to ask, how if you had a quad package op amp,
Quad op amp. Yeah.
and you wanted to separate out the power inputs to a different part, so you're not placing those over and over, so you just have 5, 6, 7 on each gate, for example.
Yeah.
How do you draw that symbol? Because it's going to have a different symbol for each gate. Does that make sense? Like if you made
Can we do the example with 2? Would this work?
Yeah, that works. Yeah, so if you want to separate 8 and 4 out into a new pin, so you just I place my op amp symbol and I place my power line separately.
Like this? I don't know what you mean by separate.
Well, on some circuits, schematics have seen or worked on in the past, especially with microcontrollers. They'll
Yeah.
separate out. Here's all the ports E. Here's all port A, port B separately on different
Pages.
And then they'll also do the same for the power supplies. So all the power supplies on one block. So they're not all in one symbol. So when like you placed gate A and gate B on the op amp,
Yeah.
sometimes I've seen a power supply block as well.
Oh, separately.
Yeah.
Oh, right. So the power supply is essentially a separate gate, almost, in this sense.
Yeah.
I haven't seen that functionality on Proteus.
Okay, so they have to be identical.
So basically in Proteus, I don't know if this is going to answer your question or not, but that pin, once you've put a power net onto this pin, you don't need to do anything with this.
Oh, I know, but some, say you just didn't want to, probably not for this class, I guess, but probably you didn't want to put 8 and 4 on there because you know they're used by both. So
Oh, you mean just
separate out 8 and 4 to a different chunk.
right? Okay.
So you'd have a 3-pin diagram.
Yeah.
And then a 2-pin for the power.
Yeah, I've never come across that functionality in Proteus. So I'll check. I've never looked for it either. So I don't think you can put all the power pins as a separate block. You might be able to, but I'll have to find out for you.
I've seen that. So on one page you would have all the power distribution to the ICs, and then on further pages you have the signal distribution.
Well, you might put them on the same page as a different area. I see it most with big microcontrollers. But otherwise
I mean, all I would do for big micro is place these.
Yeah.
I'd just literally put the power net.
it's more so all your caps are over on the side.
The caps, I do separately. So if I was going to do a bunch of decoupling caps, I would just literally put that there and then put a capacitor in the middle of this, and then just have it close to it. So it's not, you're not saying that this capacitor is, but you could potentially put a note there to say that these are decoupling caps for this chip, for example.
Just clarity if you've got a lot of them for one IC.
Yeah, of course. Big complex stuff. There might be a way to do that. I've not had to do that yet because it's always been, it's been pretty clear on the schematics that I've done so far.
So what we're discussing now is a schematic scale, isn't it? A drawing style. So we can say, okay, this is over in this section and that's over
Yeah. It's as Joe says, when you've got a chip that's got loads of power rails, then with all the decoupling caps, you can put them neatly somewhere.
So like that then. So the decoupling cap's there, but that IC
That's what I tend to do.
Yeah. Okay.
Or put them in a corner somewhere and label them with a bit of text or something. That's what I've tended to do.
Okay.
Right. Okay. I'm going to demonstrate the second device now. So the next one that we're going to do is the transistor. I'm going to do one of these transistors. So I'm going to choose the MMBT3904, and we will see whether the package associated with it is actually valid or not. There you go. Why it's not working? So I have to choose this. Right, so I'm going to drill down into the final category that we want. All right, and then I'm going to, now on Farnell you can sort by availability, which is what I always like to do. I like to sort by availability, but you can. So in stock, and sometimes normally stocking is a good one to have as well, which will at least get rid of the ones that you can't get. Yeah, it's a bit frustrating that you can't do it on all of these websites. But anyway, we want an MMBT3904 transistor, and the one that I've actually chosen on the other schematic was this 215 version, so comma 215 by Nexperia. They've got 45,000 in stock and they've got 1.6 million on order, so they're quite well used. So I'm going to open the part, get rid of that because we don't need it, and fortunately we've got the data sheet again. So now, it's not the data sheet, that is it? Yeah, it is. Okay, cool. So what we're going to do is we're going to go back to Proteus. We're going to go through that same process. So custom component fields, copy that, open the part, paste that in there, right click, make device. So this one is a BJT, it's an NPN, it's got a 40 volt collector emitter voltage, and because I can remember, I know it's got a 200 milliamps current capability, and that's all I'm going to put in. So again, this is searchable.
Do you have to put a small m?
Right, so in this field only, this is a unique part of this field only, you can't put full stops and you can't put small letters either. This field is only used in the library because full stops are used, Proteus uses full stops to denote something different in here. So in this case, I would have liked to put a small m, but you can't. Reference prefix Q for transistors, we're all good there. That is standard. We don't know whether this package is right, so we need to check this package. Now, I've gone into add edit, and then I'm going to click add, and then we're going to potentially find a new package for it. So let's just double check the datasheet. That's our pin out. So we've got 1, 2, and 3 in this configuration, and that's looking down on top of the device. So this is the package that we use. I don't think there's any other packages in here. That's it. Okay. So there's a few things that we want to check here. So in Proteus, the pin pitch is actually between this pin and this pin. So as you can see, that's E1. So we look at E1, and we've got a 0.95 pitch between that one and that one. And we've got 3 pins. Now in Proteus, the way to search packages, SOT stands for small outline transistor. That's something you just got to know. These are very, very common packages. And in fact, it'll say it in the datasheet as well. It'll say SOT in there. If we want 3 pins, we can put -3. And what that does is, at least each one of these fields, when separated with a space, gets searched independently in all of this information here. So I'm searching for SOT, and I'm searching for -3. The -3 picks up all of these IPC packages. IPC is a standard. So when you can use an IPC package in a part, do so. Search for it. It might take a bit longer, but it's worthwhile. So as I said, the pitch that Proteus uses when searching IPC packages is from pin 1 to 3. It's this little mini pitch thing here, and that was 0.95. So I'm going to search 0.95. Now these are all 3-pin packages. Can you see in the bottom left there? These are all 3-pin packages with 0.95 pitch between pin 1 and pin 3. So we want to choose the right one. So the next part that we can look at is looking at the dimensions of the body. So we've got 0.5, 0.3, 0.1, we've got various dimensions that we can use. So we quickly check in here. So we've got a length of B, which is, what?
D, I think.
Was it? D, sorry, yeah, you're right. Thank you. So it's between 2.8 and 3. Now you might not get bang on, accurate things here, but if you can get close, you're good. So we've got a 2.9 there, so we can check whether, can you see that? 2.9 width. Let's look at the other dimension, E, is between 0.12 and 0.14. That's pretty much, we're good there. And the height, you might not necessarily match the height identically, because some heights are slightly different. But A, so it's about 1 millimeters height, but this is saying it's 1.35. But that's fine. The height is, as long as you've got the length and width, you're all good. So we're now confident we can use this package because we've checked all these dimensions, and it works out. Now you want to check the pins. Now that's pin 1, that's pin 2, and that's pin 3. And on here we're going base emitter collector. So we want to check that. I think it's at the top of the datasheet. And we have got base emitter collector. Excellent. We are happy with that. Okay. Now I've got the old package in there. Oh no. These are so similar. These things happen. So what I'm going to do is, I don't know which one was the correct one because the naming of them was so similar. So I'm just going to very quickly re-find that. So SOT-3. And we should be able to find the one which has got a pitch of 0.95 millimeters pins. And then, which one was it? Was that it?
I think so.
Yeah, I think so as well.
Yeah.
Yeah. Cool. Right. That's okay. Base, emitter, collector. Good. Right. Package done. That's the hardest part of this process, is getting the package right. Then we can start filling the values. So this is an MMBT 3904. Voltage is, was it 40 volts? Yes, thank you. Its current was 200 milliamps. And its power, because I just remember, is 250 milliwatts. Tolerance does not apply. Let's put a dash in there. Manufacturer is Nexperia. The manufacturer part number, I don't know that. I did know actually. Stockist is Mauser. Stockist part number is that. Special, nothing. Generic, no. So I've skipped past the ones we don't need. Now, this says Fairchild. I'm just going to put no manufacturer because we don't need it. We're not using that DigiKey number. I don't know what AMP stands for, and it is a SOT23 package. And which library am I going to choose to put a transistor in? Semiconductor. Excellent. So that's the old one. I'm going to place the new one because you can see on the left of the screen I've got the BJT NPN 40 blah blah blah. That's my part. Double click it just to double check. Excellent. Right, that is 2 of these parts done. So we'll start with the capacitor. I'm going to bring that over this way. All I'm doing there is holding down the button, the mouse, and that's good, the accurate description. So bipolar cap. You remember on the previous slide I showed you that there's, oh, you might not have seen actually. There's polarized cap and non-polarized cap. So this is bipolar. It doesn't matter which way you connect, positive or negative. What we need on the design is we need a 100 100 nanofarads and 330 nanofarads. We need those 2 capacitors. So how do we go about searching, for example, I don't know the part number this time, you know what I mean? I can't just put the part number in there. So the way that I prefer to do it is drill down in the menus and then categorize your parts when you've drilled down. So the first thing is to go to passives. Okay, it's always called passives because they are passive. And then you go to capacitors. Same when you're looking on eBay as well. Drilling down via the categories gives you all the results in that category. So you get more hits.
If it's the same as eBay, I'll be great at this.
Yeah, exactly. It's just exactly the same thing. So we still need to drill down. You can also see which capacitors are common and used often by the number of capacitors in each category. So you see there's 52,000 silicon RF caps. There's 500,000 of those. There's 100,000 of those. Same with the ceramics. So MLCCs is what we need. It's the same as a ceramic, apart from its multi-layer ceramic capacitor. It just means that MLCCs are the small little bypass caps, the surface mount ones that you see all over the place. Leaded or surface mount, we're going to go for surface mount. There's also 383,000 different ones of these. Loads. So now we're going to use the parametric search to drill down to find the capacitor that we particularly want. Okay? So the first things first is we know what capacitance we want. It should be scientific. It never is like the scientific notation. It should really be 100 nanofarads. But 100 nanofarads is the same as 0.1 microfarads. We are going to go for at least 50 volts. So I'm going to click that and then there you go. Select all those. The dielectric, I'm going to go for X7R. Now, in other applications, you might need different dielectrics. Because this is an electronics course, I'm not going to go into all the detail of what the different dielectrics do and all that. But if there's appetite, I will go through and create a different lecture on what all this means, because capacitors are quite confusing.
Don't pick Wi-Fi.
Never, like, ever. Then what else do we want to know about it? So where's the, yeah, so you see here in stock and then also normally stocking. Can you see the results remaining is just getting less and less? And then the case size, I want an 0805 cap. So I'm going to click 0805. We've only got 246 left. Don't click that.
What was it? 0805. 0.08 of an inch by 0.05 of an inch. There's also the metric ones which use the same dimensions, and it's really confusing.
Yeah.
Oh, it's like an 0805 imperial, like an 0603 metric. There's also an 0603 imperial. It's really.
It is.
Is it the same across all the suppliers, or is it because Mouse is American that they use?
No.
No.
0805, 0603, 1210, 0402, 0201. They're all like standard electronics package sizes. And you typically do use the imperial version.
It's about 1.0 foul.
Yes, they're all based on thous.
Mil, which isn't a millimeter.
Yeah, oh
It's
god,
also
but
same as a foul.
it just, you get used to it. When we go to the layout side, when we start actually building the circuit in Proteus, once all this faff's out of the way, because this is faffing really, but it's really important faff, you'll see that we do things in metric grid and we do things in imperial grid. So there's two different grids that we use and two different ways that you need to kind of be familiar with at least. So what I'm going to do now is Mauser has sort of, well, you see, there's 2.6 million of these capacitors in stock, which is loads, isn't it? And then they've got 1.5 million of these in stock as well. Because I can't sort by availability, which is annoying on this website, but you just have to then look to make sure that the part that you chose is nice and available. I'm going to go with the top one. It's a 10% part, which means plus and minus 10%, not 10% absolute, which is a big difference. So now I've found my part, okay? I've got my symbol here. So I'm going to just literally right click, make device. This one should be pretty simple. So the way that you do capacitors and the way you do resistors and all these other devices, really, where you don't have the part number at the end of this search. You don't need the part number in here. What do we need to know about the cap? We need to know that it's cap. We need to know that it's ceramic. We need to know its value. Oh, this is another point as well. Because you can't do full stops in this particular box, if you wanted to do 10.3 nanofarads, yeah, you put the NF where the point would be.
Yes, that
Yes, exactly. So this one's 100 nanofarads. It's 50 volt. Is it 50 volts? Yeah. And it's got a dielectric of X7R. That'll do. So if you always put your capacitors, that information in as capacitors. So what? It's a cap. It's the technology, the value, voltage, the dielectric. Then we're all good. Add edit. This is the easy part. Okay. I'm going to delete the existing package because that's just the one that came with whatever I chose randomly from the part picker. And I'm going to go 0805. There's a few different 0805 thingies here. There's 0805 cap and 0805 resistor. There's no different. I've not been able to find any difference between these three footprints, so I just always choose just bog standard 0805. So 0805 done. It's very slightly different. The Proteus ones are slightly more giving. There's slightly more.
It's the density option ones either. Is it the footprint density and standards as well?
Yeah, I mean, I've never had to. I'm sure if you dive into these packages, you'll be able to find more detailed versions of them. But for all intents and purposes, for our needs, particularly in this course, 0805 is absolutely fine to use. So assign package, job's done. Primitive is a simulation property that we don't need. That's a leftover from the default thing. Right. What have I forgot to do?
Copy and paste your text in.
I forgot to copy and paste the text in. So you'll do this because I've just done it. It's easy to forget. So the only two things that I know here is value and package. That's what's kind of default comes with it. So 100 nanofarads. I can put the small n there. Package is 5. Okay. Don't care about the data sheet. I'm going to change the multi-layer to what it is, X7R, and it's not by TDK.
So you just put none.
Yeah, I tend to. It's a bit. You can put it in there, but we know the manufacturer because we've already typed it, and it's not 1210 size. It is 10%, but it's plus minus 10%. You need to make that distinction. And we're going to get rid of that. Get rid of that. Get rid of that because it's all information that we've got. So it's going in the caps library. Okay. Now I've got my capacitor. I've deleted that existing one, placed a new one, but it's got no information on it. So copy. This is where you can do it really quickly. Paste it in there. Right click, make device again. If you don't change this name, it's going to overwrite that device in the library. Okay. So if you ever want to make a new device, if you change anything about that name, it's going to make it a new device. If you don't, that's where it, yeah. So if I keep that the same, I'm going to overwrite the same thing. So I'm going to click next on there. Now all these things are there. Change the package to 805 because it made it not checked. I also did it with that as well. 100 nanofarads. Voltage we do know, and this is the case where current is not applicable, but power is also not applicable. Tolerance is, and it's plus minus 10. The manufacturer was, can't remember, Kemet. Manufacturer part number is that one. Goes in there. Stockist mouse it. You'll get very familiar with doing this.
You're very quick at copying.
Yeah, I've done it so many. If that happens, it's because you see that tiny little.
Oh yeah, space.
Yeah, if you miss that, then it works. Special. I tend to put the dielectric in there actually, so I tend to put the dielectric in the special column, and then it's not generic. Next. It goes in. Oh yeah, you've already done this once, so you don't need to change anything. Now it says it already exists. Do you want to overwrite it? Yes. And then do you want to update all the components on the sheet? Click yes, but sometimes it doesn't work anyway because if you double click it, it's got all not checked in there. So you can just delete that one again, click it, and then there.
How come you've not marked that as generic?
Because I could have if I wanted. Say again.
I just said, but yeah.
Oh, sorry, I didn't realise you said that because I thought it was Joe. No, with some capacitors you can. With bypass capacitors, you generally can mark that as generic, and some resistors you can as well. But to not complicate things, I've decided to keep it as.
And all that does is stops the manufacturer of the board sorting it out for a
different part. Yeah, but you are correct. So in that case, this particular part, because it's a bypass cap, and we've already filled it with all of the important details, we can actually set that as yes. This time, we're happy for that to be generic. Don't save yes in the library, in that field. Only edit. So when I put yes there, I've only put yes to this particular part on the schematic. I've not saved it in the library. Because it's on a case-by-case basis. Now, in answer to the question of how to remake something that's quick, without having to do all of that faff again. So what I'm going to do now is I'm going to find a 330 nanofarads part. Yeah, thank you. I was looking for that actually. So capacitance 3.33, okay, and then we've got 43 of those, nice and quick. All the other things are the same, and then we find one that's got plenty. That's 12,000, 100 and odd thousand. Let's choose the 100 and odd thousand one, and we found another part. So all I'm going to do now is right-click the existing part, click Make Device, and then remember what I said about changing this. Now I've made a new part. That's created a new part. We know it's the same footprint, and all I need to do now is put 330 nanofarads. Package is that. The voltage is the same. I'm going to copy the thing. That was a stockist number, wasn't it? Oh, come on. It's that little space again. Mauser number. It's in from Mauser. The manufacturer part number is that. It might not work that. It didn't work that time. Why? I don't know. Murata. And that's it. Is it still 10% actually? Yeah. I just did something that I told you not to do, didn't I?
I was just about to tell you that. Cost most himself.
Yeah.
That was a lucky guess.
And these can stay the same. Good. Right. Next. Caps. It is ceramic and it is 10% and it is X7R, so that's all still the same. We just created a new device. So when you can do that, it speeds the process up just
Yes.
tenfold. You know what I mean? Way easier. Decent. Right. I'm only going to demonstrate one more now, and then we are done for this week. Okay.
I'll put a head off Dan. Thank you.
Yeah. No problem. That's fine.
Really, really good.
No problems. So this one is more complicated than the others, and I will show you why. So this is the pickaxe socket. I'm going to copy this code, and I'm going to try and attempt to find it on the internet. I'm going to say attempt. I know I can because I've done it. Okay, so con 0339. Right. This is the part. The data sheet's not very good. There's information scattered all over the website. So what I'm going to do is open the data sheet and open. So I've gone to resources and I'm opening these two diagrams. This is obviously a modern diagram. This part was originally made in like the 1987. That was the year that I was born. So what we need to check is the default footprint okay, and are the pins right? So the package that this comes with is called pickaxe socket. I'm going to copy that, go into PCB layout, and I'm going to go into the package mode, this little chip looking thing. Click P, and it obviously opens onto the wrong thing. And then go to that, click pickaxe socket, and then you can place it on the schematic somewhere. That's the package for this device. Now, the dimensions are about correct, but they are slightly off. But because the pins are thin, Proteus, the guys who designed this package, will have checked this. They will have built this. So we can see between these two back pins, we've got 2.2 mil because it's all referenced to this 1 mil line here. So what you can do is click the line tool, and then go to that pin. And then when you hover over the middle of this pin, at the bottom, oh, you can't see it. At the bottom, you might need to make that a bit bigger. Click that. See, it says 2.54. You see that at the bottom? That's the length of this current line. And that's 2.2 between these two pins. But because the hole is quite large on these, I'm pretty sure it's going to work. And then we can do it for this pin to that pin is 7.62 millimeters. And that says 7.7, so very, very close. And the last one is 10 millimeters pin to pin, and that's 10.16. So it's very, very close. Usually you would make a footprint that's bang on that part, but because I'm using a default library footprint, again, I'm pretty sure it's going to work in this case. So this is designed not to be used as a headphone socket. It's designed to be used as a digital communication. So there's no left, there's no right, there's no ground. How do you know what pin goes to what on the headphones? So I'm going to decompose this. So what this means is I'm going to take an existing part and I'm going to break it to its constituent components. Decompose at the bottom there. Now this is turned into a bunch of lines. It's just nothing. Well, not nothing, but you know what I mean. It's just a bunch of. It's not a device anymore. It's graphics only. It's graphics and it's pins. So you can edit the pins directly now. So what I'm going to do is go back onto the data sheet. Now I'm extending this a little bit to make it so you can have this box there. I'll go back onto the data sheet. I'm going to check what pins are connected to what. This is not a very good drawing. This is better. This is why the pickaxe guys have done this drawing. So this drawing, you can see, this is called tip, that's called ring, that's called sleeve. And I know, because I've Googled it, left channel is the tip, left, middle, the ring is right, and that's ground. So I know that that is ground here. So that one pin there, the serial out pin, is ground. Now what's the number on the component? Pin number 1. Pin number 1. Double click the pin, and you can put GND in there. This is for my information only when I'm wiring up the schematic. The other thing that this website advises, if you read it, please note that each pair of pins marked B and C in the diagram must always be joined together as shown. Joined together as shown. They're actually switches, internal, D and F, G and E. This is the hardest part. This is why it's confusing. They use numbers, they use letters. It's confusing. But these are detect switches. We're not going to use that functionality, so we're just going to short the switch out and use it as is. So we need to continue and determine. So if our ring is right, B, if you're looking, so above view, it's these two pins at this side. So we go back onto the layout, these two pins above view, same view, it's pin 2 and 5. So we've got pin 2 there. If I put 2, 5, that's going to connect those pins permanently, and you'll have to put a track between them when you come to pin it out. So RxD, I said right, didn't I? That's the right channel. Okay, I'm doing this quite quickly because I know that I'm running over time. Pin 3, what we need now is hopefully, I believe, the ground channel. A. No, it's the... Well, I just confused myself. Left channel. So, pin 3 is the other side of this block, okay? And the other side is C. C is the left, because I know that the tip is left. So, I need to connect pins 4 and 3 together. 3, 4, that is left. Whew, right. So now I've kept the original. You could have deleted these, but I just wanted to keep them there just as a sort of information. This is now ready to be made into the part that we want it to be. You see this invisible box? It contains all this information. Remember that thing that I did at the beginning? I made the things invisible. Text styles, properties, visible. This text thing here, this is actually information about this part. If you, I'm going to hide that again. If you make the device like this, you see the selector box doesn't encompass this invisible box here. If I right click make device, there's no information about it. It doesn't know it. It just thinks it's a brand new device. If you make sure that you include this invisible box in the selection, it's invisible now because I've made it invisible, but it's not if you don't. It includes all the information about the actual device itself, so just want to bear in mind. Right, I'm going to call it jack. I'm going to call it 3.5 millimeters, which is 3M55, and I'm going to call it TRS because it's a tip ring sleeve jack. And then the reference designator, I'm going to call it J. J is the least movable part of a pair of connectors jack. The plug is the more movable part of a pair of thingies. The pickaxe socket, you see that it hasn't assigned these pins. They're all purple. What you need to do is, because we're remaking a part, you need to actually delete the package and then reinitialize it, and these pins will be filled in. Because we've got the pins on the device, and we've got the pins on the footprint. So if we delete that, and then we simply find the same footprint, pickaxe socket, and then we press OK, you'll see, bang, you see it's filled them in. Now we know that pins 3 and 4 is left, pins 2 and 5 is right, pin 1 is ground, we can assign the package. I've forgotten to do the thing. So delete mod file because we don't use it. Delete code because that's just the manufacturer's code. We add our own. Make the device. You can keep that datasheet there if you want. I don't know even if it's used. And where we're going to put this? Con. Yes. And it's not an IC, is it? and it's not that anymore, it's a connector. So it's a connector, and it's an audio connector, so stereo TRS. Let's put TRS in there. Okay, good. Right, nearly done. Connector done. Right, delete this, because this is not even a device anymore. It's just a bunch of like stuff. It's what a device can be. It's got the potential to be a device. Right, delete that. Place. So you click into your part picker. Place your actual device there. Excellent. Right. Copy all that lot. Put it in there. Right click, make device, and we can keep everything the same. Change the package to the pickaxe socket, because that's what it is. The value is 3.5 millimeter TRS. Voltage is, we don't know. It says 250 volt standoff voltage in there, but you wouldn't really put that. Not applicable. Not applicable. Tolerance not applicable. Manufacturer is pickaxe. Caps. Manufacturer part number is Con 039, I think, was it? Yeah. The stockist is pickaxe again, because you can't get that from Mauser and Farnell. Stockist part number is special, nothing. Generic, not this time. Remake it, just click next and press OK. Update the libraries, but I always delete that one anyway. Place a new one. Job's done. Right. Just to very quickly round off. So we've done all of that. We're happy. What I would like you guys to do is take the schematic that I've just done here. I'm going to email it you all, and I'd like you to make the remaining parts on the left-hand side. You can use me as a resource. If you get stuck or something's confusing, then use me as a resource. I'm going to send you this video out, so you'll be able to go through one or two of the ways that you can make these packages. But I've given you hints and tips. So find that transistor on Mauser, find these on Farnell or Mauser if Farnell isn't working by the time you do this. And I've given you the package as well, just to make things a bit easier. So that one's the same package as the MPN, but make sure you check the pins. That's a TO220 package. This one, when you search it on Farnell, it says it's got a package of DO204AH. What I'm telling you here is that the DO35 package in Proteus is the same type. You can go onto the Wikipedia page and also check the diode packages, and that's where I found that information. Consil 2 doesn't need any work. We've already moved that over because we're just using that as a PCB feature. And then I'd like you to add a new part yourself called Consil 3. Find the part in Farnell. It's just a 3-pin pin header. That's the exact picture. I took the picture from Farnell. And then that's it. Next week, we're going to do some more. We're going to finish the parts next week. So we'll make the generic resistors that we can use. We're going to put an LED, the DC-DC converter for power conversion. We're going to put a potentiometer so you can actually change the volume. We're going to have the DC jack to power it so you're not running out of 9-volt batteries. And then we're only going to wire one channel because there's a special trick in Proteus where you can duplicate the parts and the layout at the same time, so you're not doing the same thing twice. We might do that actually, we might not. So again, apologies, I've not highlighted questions. This was so long. There's a lot of information to get through. I'm going to give you the videos and I'll give you this Proteus schematic to start with, so you've got something to reference on your computer. So yeah, that's what we're going to do. Any questions, anybody?
We also do what you've done today.
You can,
and then do this exercise.
if you want, or I can give you my schematic I can give you the one that I've just made there, so you can start with at least the baseline. So it might take a very long time if you're going to do all of that.
Okay. Yeah,
I did it relatively quickly.
Yeah.
I could have done it quicker, but you know, to start from the beginning. If you want the practice, by all means, do the whole thing.
That's fine. Good. Thanks very much.
We all good?
Brilliant.
Excellent. Well, thanks a lot for putting up with such a long one this week.
Good. Thanks.